In this video, we're going to put together what we've done the last few videos, and we're going to solve exponential and logarithmic equations. So we have solved some exponential equations before, namely by the procedure of relating the bases. We had an exponential function where both sides of the equation could be written as the same base. For instance, we might have seen 2 to the 5x is equal to 1 over 4 to the x. In this case, both sides can be written as powers of 2. So we related the bases and then set the exponents equal. Well, now what if we can't do that? What if instead we have something like 1024 is equal to 19 to the x plus 4? Well, first of all, we know we cannot relate the bases. We cannot write both sides as an exponential to the same base because we see addition here. So let's start by subtracting that 4. And we have 1020 equals 19 to the x. Well, is 1020 a power of 19? The answer is no. So, we cannot relate the bases. What are we going to do instead? Well, we have two options. The big thing is we need to make sure this exponent gets out of the exponent. This variable needs to get out of the exponent. We can't do that while we have exponentials. But if we had logarithms, we can pull the exponent out front. So we're going to take a logarithm of each side. And here's where we have two choices. Your calculator only knows log base 10 and log base e. Now I could take, let's say, log base 19 and then do a change of base formula on it. But that's going to be the equivalent if I take the natural log of each side. My preference is the natural log. The common log works just as well. So I'm going to go ahead and take natural log of 1020. Well, that has to be equal to the natural log of 19 to the x. These are functions. Up here we said that 1020 and 19 to the x are the same thing. Well, natural log is a function, so if I plug the same thing into it twice, I should get the same thing out. So I can take the natural log of each side. Notice I am not multiplying each side by the natural log. There's no natural log to multiply by. Natural log is a function. It has to have an input. So I am putting the left-hand side into the natural log function, and I'm putting the right-hand side into the natural log function. Since they were equal before, and this is a function, it's still equal. But now I am taking a natural log and raising the inside to a power. So by that power rule, it can come out front. So we have the natural log of 1020 is equal to x times the natural log of 19. And now the natural log of 1020 and the natural log of 19 are just numbers. I might as well have something like 5 equals x times 3. What do? We'll divide both sides by the natural log of 19. And so we get x is equal to the natural log of 1020 over the natural log of 19. And if you are asked for an exact answer, that is your answer. Of course, that's not very useful. Very few of us can get a good approximation on that. So we can go type it into our calculators, and we will find this is approximately equal to 2.3528. Notice I did round. It would actually keep going, but we rounded to make things, well, so that we could actually write it out. So round however far you are asked to round. Well, that's an exponential equation. What about a logarithmic equation? Let's try something like log base 2 of x is equal to 4 minus log base 2 of x minus 6. Well, here my problem is variables are inside logarithms. I really want to get them out. The easiest way to do that would be to rewrite this as an exponential function. If I rewrite it as an exponential function, whatever is inside the logarithm ends up on the other side of the equation by itself. The problem is, in order to rewrite it as an exponential function, I need to have this equation in the form of log base b of m equals c. And I've got logarithms on both sides. So I'm going to start by adding this one over. And we'll have log base 2 of x equals, oops, not equals, sorry about that. Log base 2 of x plus log base 2 of x minus 6 is equal to 4. But I'm still not in this form. I have two logarithms. But we remember from last week, if I add logarithms, it's the same thing as a single logarithm where the insides are multiplied. That's the product rule. So this left-hand side is really log base 2 of x times x minus 6. And now I'm in that form, which means I can rewrite this as an exponential. And as we recall, it's the same thing as saying b to the c equals m. b is my base, c was on the other side, so it's now inside my exponential. m was inside the logarithm, so it's now by itself. So this is the same as saying 2 to the 4th is equal to x times x minus 6. And this is just a quadratic. So in order to solve a quadratic, I need to get one side equal to 0 and factor the other, which means the fact that this is already factored is a problem. So I'm going to multiply this through and add 2 to the 4th, which is 16. Well, I'm going to subtract 2 to the 4th, which is 16. So we get 0 equals x squared minus 6x minus 16. And this factors. That's x minus 8 times x plus 2. So x minus 8 equals 0, which means x equals 8. X plus 2 equals 0, so x equals negative 2. Oh, but we've got a problem. What's the domain of a logarithm? 0 to infinity, but that's non-transformed. This one's been transformed. This one hasn't, so its domain is still 0 to infinity, which tells me that negative 2 is a problem. It's outside the domain of the original, so I have to throw it away. How about this one, though? X minus 6. Well, to find its domain, I need x minus 6 to be greater than 0, so x must be greater than 6, which means I can only take answers that are greater than 6. Negative 2 was not, so it's, well, thrown away. However, 8 is, so we can take this as our solution. That is one problem with logarithmic equations. We have to check our solutions because, well, sometimes we get a bad solution. Just like if you remember when you were solving radical equations, you might get a bad solution. When we condense the logarithm, we potentially created false solutions, and in this case we did. So we have to double check. Most areas in math, checking is just, let's feel comfortable about our work. In logarithms, it's, let's make sure we get rid of the extra solutions. And how about an application? Let's say we've got a certain country whose population increased from 19 million to 22.6 million in 10 years. Assuming this trend continues, what will its population be in 20? Well, what will its population be 10 years from now? So 20 years after that 19 million. So in other words, we've got year 0, population was 19 million. Year 10, the population was 22.6 million. And we're asking, year 20, what's the population? Well, let's create a model. This is exponential growth. So we have P of t, the population at time t, is equal to the initial population times e to the kt, where k is our rate of growth. So how am I going to find that? Well, the big question first is the initial population. That's 19 million, so I can toss that in. K, I don't know, but I do know after 10 years, it has increased to 22.6 million. So I can solve for K. I'll do that by dividing by 19. Take the natural log of both sides. Remember, natural log of e to a power, since natural log is log base e, those cancel out and we're just left with that power. So k is equal to the natural log of 22.6 over 19.0, and all of that over 10, which is approximately 0.01735. That means our population model is equal to 19.0 e to the 0.01735 t. Now, if I want to know the population 10 years from now, that's when t is 20. All I have to do is take this model and plug a 20 in for t. So we'll look at p of 20 is equal to 19.0 e to the 0.01735 times 20. And if we plug that into our calculator carefully, we should get 26.9 million. So my challenge on this week's video is let's solve the same problem, but instead the population grew from 22.9 million to 23.7 million in 10 years. Find the population 20 years after the start. Thank you for watching.